Okay, so welcome everybody. First of all, I would like to thank the organizers for giving me the opportunity to talk to you today. I'm the second part of our afternoon experimental session, so I just would like to know the audience a little bit. Can we start with a quick exercise? Who self-identifies as an experimentalist? Okay, so that's about maybe 1/3 to 2/3. Okay. I guess by exclusion, the rest doesn't. Okay, good. I just somewhat give you a mix because what I'm trying to do is tell you a very elementary story in topological physics, and so there will be lots of theory and experiment. So this is really good. One thing I just wanted to mention in the beginning, some of the key people of some of the things that I'm going to show you, but this is not really about our stuff. I want to advocate them because they did fantastic work. So there's Mark. He's fantastic. He works with us at EPFL and now in Hamburg. There's Aris at Urbana-Champaign. He did a lot of the theory that I'm going to try to explain you to the best of my capability. Claudia's group made a lot of crystals, as did Eric Bau and Philip Ronnen at Los Alamos. Okay, important people said. So, my PhD advisor in his condensed matter classes, he always had one very good question for oral exams for advanced solid-state physics. And so he was very much a materials person. He had lots of stuff. And he would take a crystal and give it to the student and say, look, can you tell me what this is? And the students, no, this is a piece of stuff. What is it? And so, of course, the question was then, what could you do with it? What are the physical properties you could measure it? How could you actually figure out what I just gave you? Of course, you could do very elaborate analysis on the atomic level and figure things out, but you could look at the conductivity, you could look at the optical conductivity, you could look at the magnetization and things like this, right? And so that will give you the most important response functions of the object that you have in your hand. And so being a transport person, something that's very important to tell you whether or not you have a metal, an insulator, a semiconductor, is a resistivity. The beautiful thing about this is that we have these gizmos. We have a multimeter, and you could just poke it into that thing, and you see, yeah, this is a good conductor, bad conductor, yeah. Is there something like this about topology? Is that even a meaningful question, right? So can you give me a piece of stuff, and I could tell you, yeah, this must be topological in some sense, and how does that impact its macroscopic observables? So this is the main story that I want to discuss about. So what are the actual macroscopic physical observables that are really dominated by topology? Or do I always need a synchrotron and do ARPAs, and then I can see a band crossing, and that's how far it goes? And I think this is a very important question for two main things. The first one is experimental observation of materials. So I would say in our field, we've somewhat exhausted a little. I'm trying to not insult a lot of people, but we're somewhat exhausted single particle topology. I think we've classified what there is to classify. We've seen what there is to see. You now find another 3D Dirac semi-metal. You're likely not going to write it in Nature. So these types of things. But there's a lot of interesting things of topology plus X. Topology plus magnetization is very important in applied physics right now. There's topology and interactions in correlated topological systems. What is the meaning of topology in, let's say, quasi-particle excitations of, say, a quantum critical system? Things like this, where maybe we don't have a band structure, so we need something to begin with to actually figure out, is this a meaningful question? What can I tell? So that's number one. Number two is some of the relevance for real-world applications, because really, if I can't measure it, I can't use it. That's a generic fact, right? If it's so weak that I need a lab to figure out that this is the truth, then this is great, interesting physics, but applications are kind of walking out of the room at that point, right? So what is it? What are the bulk things that are really macroscopic observables that come from topology? This is what I want to address, and I want to talk about three specific cases. One is a magnetic anomaly in the quantum limit. I'll tell you what this is. I want to talk about phase-sensitive detection in terms of quantum oscillations. And I want to tell you something about their temperature dependence. So this is what I would call hunting for topology. I'll start this with a somewhat historic overview of my own entrance into this field. And so I came from somewhat of a different path. I got really interested in this on a material that people mostly study in the heavy fermion community. It's lanthanum rhodium 5. It's a really complicated metal. Forget everything I'll tell you. It's not important. It's just the most important thing is this is very complicated. It's complicated for trivial reasons. It just has 2 independent indium atoms on the Vikov side. It has rhodium in there, lots of 4d orbitals, massive orbitals. The lanthanum doesn't really very much contribute, but there's just orbitals all over the place. So a vanarization needs, I think, 23 orbitals. And so the thing is just complex. And because of that, it gets it. Besides that, complexity is a vegetable. It's non-magnetic, electrons are light, single particle. Okay, it becomes very interesting when you put cerium here, but that's a different talk. Okay, so people study this just as a vegetable. Now there is one interesting experiment that somewhat caught my eye, and that's this. So people measured of this vegetable metal magnetization as a function of magnetic field. So what you see is very strong oscillations on top of a diamagnetic background. This is good. Most metals are diamagnetic unless there's some magnetic moments. Okay, fine. And then you hit the quantum limit of this thing. So you look at these oscillations. The quantum limit in this case means that only the last Landau level of this tiny pocket is occupied. And after that, you see that there's a massive paramagnetic magnetization over an insane field scale. Very, very high magnetic fields. So why is that? What happens here that is a tiny pocket suddenly turns a diamagnet into a paramagnet? And how does this get this huge paramagnetic response? Somewhat of a strange thing. In particular, it is strange. Oh, and you can look at the quantum oscillation. So all of these other Fermi surfaces at much higher fields and in other techniques, you can resolve them very well. So they all exist, these crazy bands that I've shown you. I don't think there's particularly much physics about this. But the point is that if you have something that looks like this, 10 to the 23 carriers per cubic centimeter, decent bulk metal, the magnetization comes from this teeny tiny blob, 7 Tesla wide. That's 0.1% of your boson. It's a tiny pocket, and that gives you a huge paramagnetic response. It's very strange, right? And it sounds not just strange, it's almost outright impossible. So imagine that you have a tiny pocket. Now you can think about your doped semiconductor of choice, silicon with a little bit of phosphorus in it. So you'll have somewhat of a parabola. Parabola will be barely filled because of tiny pocket. You apply a magnetic field. What will happen is that you will Landau quantize this problem. This gives you an harmonic oscillator, as Dima has very nicely shown us. So then you get the dispersions of this harmonic oscillator. But now, as you increase the magnetic fields, they will move up, right? So the energy depends linearly on the magnetic field. So even the lowest Landau level, all of them, they move up. And because it's a metal, mu won't change. So actually, you would expect this thing to become empty. It's electron-like, we know, but it doesn't really matter. Holes do the same. So then they're completely filled. So what goes on? This thing is dead. For everything we know, this thing is dead. How is it magnetically not dead yet? Very strange, all right? Can't be. So that actually brings me to a very interesting paper from the very early days. So this is 2004, well before. Okay, topology already was a thing, but semi-metallic topology was not. There was this paper about the Berry phase and the de Haas van Alphen effect in lanthanum rhodium indium 5. So I kind of updated this paper. So nowadays, this would clearly be Nature, and they would have replaced the word of band contact line by nowadays you would call this a Dirac nodal line. So their whole point is that they found an effect of Berry phase in a bulk solid, and they could just use a Dirac system, nothing else, just the Dirac system, to explain this magnetization data. So that's their Dirac prediction. So now, this I would call a very interesting response. If I have a Schrödinger-like electron system, it would be dead. All right? I only see all the other 10 to the 23 carriers. If they are Dirac fermions, I have a chance to actually observe them when they are in the lowest Landau level. So the lowest Landau level physics is very different between these two cases. And that's what I want to discuss and tell you why. Now, there's somewhat of my take on things. So we've seen from Dima how relativistic electrons have a different dispersion for Landau levels than trivial electrons. So in the relativistic ones, they also form one-dimensional modes along the magnetic field, but only if n is 1 or larger. So for all of these, this will essentially give you these shifted square root functions. But if n is 0, this term is dead. And essentially you find that this mode is parallel to k. I only plotted one. If it's Dirac, you also get the counter-propagating one, and you get two modes back, a positive and a negative one. But the main point is that this lambda level is really fundamentally different from all the other lambda levels, whereas these arguably look very similar to those that you would get from a quadratic dispersion. But the lowest lambda level, the n equals 0 lambda level of a harmonic oscillator, is still a parabola. There's nothing special about it, right? Okay, maybe then you get quantum effects, you go, and things can change. But at least on this level of quantization, they are the same. They're all the same. And this is the main difference between these two. So if you now go into this lambda, into this quantum limit, then really here you're in this one-dimensional dispersive mode, whereas here you're really just stuck in this last parabola. So, yes, please. Sorry? This is for open boundary. Am I considering surface state? This is all bulk. So yes, open boundaries, periodic boundaries. So this is about bulk transport of bulk 3D semi-metals. That's right. In this particular case, because it's such a good metal, there's absolutely no hopes of doing anything like what Nadia just showed us on surface transport. These are just metals, shiny, highly conductive metals. All right. So how does this now work? Actually, there's a very simple explanation for this. If you go to the low enough limit, then you don't really have to care very much about the differences between internal and free energy. So if you just think about the zero temperature ultimate high field limit, then you will see that since the magnetic field drops, there's a main difference of the derivative of the state, of the energy of the state with the magnetic field. Namely, in the relativistic case, this actually becomes 0. There's no more dependence of the state on the magnetic field. For the experts, yes, there's a caveat, which is the degeneracy factor that will give you a renormalization of the very high magnetic fields, but at the level of the state, there's actually no difference. Whereas in the case of the trivial state, you do have this 1/2, which is the phase factor that Beeman told you about, and this 1/2 will keep the magnetic field dependence in, and at any magnetic field, you actually expect a non-zero derivative. So it's very clear that metals will become diamagnetic, but these will go away, right? And so that gives you a strong anomaly from the high Landau level index, low field, where you get a diamagnetic response, and then suddenly this breaks away, all right? And so one of the things that we did is to find this, or look for this experimentally, and we looked for a material niobium arsenide. So the main idea here was, if this is true, this should be the same for Dirac or Weil or any types of three-dimensional point-like topological defect. If this is the case, then we could also find this not just in exotic metals, but maybe we can also find this in very simple point-like Weil fermion metals. Niobium arsenide is a particularly famous one, niobium and tantalum arsenide. It belongs to the class of inversion symmetry breaking Weils, which is very nice because they tend to be very clean, or at least cleaner than magnetic ones, and we have quite nice examples of it. The disadvantage is that, these inversion asymmetric compounds, they have 1,000 copies of Weil points. So you don't have 2 or 4, which is nice because it's the minimum, as Jen told us. In this case, you have 24. Okay, so there's a lot of them. But anyways, the more the merrier, as they say. Still, even though there are so many of them, this magnetic anomaly still works quite nicely. So what you can do now is you can apply a very strong magnetic field. So again, you have to really depopulate all the other Landau levels. You have to go to the last Landau level. So you have to go to very high magnetic fields to reach the quantum limit. And then you can measure, for example, magnetic torque. If you want, you can replace this in a way by magnetization. It's not really quite true. It's the perpendicular magnetization to the magnetic field, not the longitudinal one. Okay, fine, but it's a measure of the magnetic response of the material, and you see a very nice downward curving response. On top of it, there's these quantum oscillations. But beyond the quantum limit, there is a change in slope, and the signal really explodes. So you get a very large magnetic response, and again, it's triggered by the fact that this thing here hit its quantum limit. And it's very important that this is not the biggest Fermi surface. Actually, it's the smallest in this problem. There's other ones at 100 Tesla, at 150 Tesla. So the whole material is not yet in the last Landau level. just this one pocket actually is, and at that point, this magnetic anomaly starts to kick in. That's actually a very interesting method to probe for a response function that's highly non-trivial in topological systems. For example, if you measured resistivity, which you can do, you will not see any of this. So there's quantum oscillations of the resistivity. Resistivity slowly rolls. That's it. There's no anomaly here in the transport coefficient. It's really truly a magnetic response function that comes from the fact that the magnetic response of the last lambda level is so different from that of the other lambda levels. And as you depopulate it, that thing starts to kick in. And now you can play with this thing because of the crystalline anisotropy. So if you like this, then listen to this. If not, zone out. It's a good time for emails. In 2 to 3 minutes, we're going to be done with this. So the torque, this particular magnetic anomaly now depends on how you apply the magnetic field with respect to the crystal. So if you apply it at a very low angle, meaning along the crystallographic C direction, it's just as it is. It happens at very low fields, 18 Tesla. And then as you tilt it to higher angles, this anomaly that you can clearly trace, quantum oscillations say stop, and boom, magnetization explodes. It goes to higher and higher magnetic fields. All right? At the same time, you can also just measure the quantum oscillation frequencies, which tells you what is the cross-sectional area of a Fermi surface at a given angle. It's essentially a tomographic view of how you slice the Fermi surface. And so this you can do at low fields, no quantum limit physics here, and you could measure it, and you see that the same thing happens. At 0 degrees, it's very small, and then as you go up, it actually goes up. And that's because these Fermi surfaces around the wild points, they're actually somewhat banana-shaped. So if you apply the field along the axis of the banana, the cross-section you will see, the extremal cross-section is this tiny circumference here. So that's 20 Tesla. But as you apply the field more in this direction, your cross-sections will grow. So the area will become much bigger, and so you see this thing go up. But the beautiful thing is that if you put both together, they really trace exactly right. So you put on one plot the angle, the field angle, with the magnetic field for this anomaly in the magnetic response, and for where the quantum limit is from quantum oscillations, they really trace each other completely. All right? So that's kind of a neat example of where you can tune now the response and the response field by just changing the field angle. All right? One thing that you could, for example, do is look at the magnetic torque as a function of angle, and you will find, if you do this at low fields, where you never cross this line, you will find one response. If you do this at high fields, as high as you can, say 60 Tesla, you get the exact opposite response. So that's your crossing over from dia to paramagnetism. Okay, at very high angles, we don't have magnets strong enough to actually do this. But if you ignore the very highest fields, then it does this. And of course, you can do more fun things, like you can go to some intermediate fields, where it starts out in one state, once you're above this thing, then it goes to the quantum limit now as a function of angle, and it has the opposite response. So really, this is a sign change, is a part of these types of physics. So, okay, I've just shown you this to convince you that this is something that you can experimentally do. And after we did this, quite a few other groups also used this method, and that actually really works out quite well. In that, there's an anomalous magnetization, bulk magnetic property of a big chunk of three-dimensional Dirac and Wild semi-metals. With Diracs, it becomes a bit difficult because now you have to make sure that there's a protective symmetry that ensures the degeneracy of the Dirac point, that your magnetic field doesn't break it. So you have to be a bit more careful. With Wilds, it works generically because they're non-degenerate. But there is an anomalous magnetization when they reach their quantum limit. And now, the quantum limit is generally, if you think of copper, silver, and so on, that's somewhat enigmatic physics because we don't really reach it, right? But for all of the relevant topological systems that we talk about, especially with the angle of applications, we're anyways talking about low carrier density, some spheres around a wild point, very small objects, as close as you can be to that topological anomaly. So this is why it's somewhat relevant to this materials class. And it really dominates the magnetism, even then when there are many more trivial bands around. So this is exactly what I was looking for and what I was talking about in the beginning, namely that we have a bulk measurement that I can stick into my magnetometer, 60 Tesla, I need a special magnetometer, but still, can stick it into my magnetometer, and I can maybe not get definite proof, but rather evidence that something interesting happens based on topology that I cannot explain with a simple, massive Schrödinger-like band. Are we tired? Question? Yes.
Is there a connection between the anomalous magnification and the emission of the lattice? For example, if you're in type 1 or type 2, is the anomalous magnification enhanced?
Yes, okay. So this is a really good point. In type 2, it's very difficult because your lambda level spectrum looks completely different in that case, because your type 2 wild point is essentially the touching point between two Fermi surfaces. So in that sense, I have to think about how this works. I think this will compensate. But actually, this is a good question. I've never thought about wild 2s for this. Yeah? Yeah?
I understand you want the bow point to be very close to the Fermi energy, that you want a small pocket. But there's no way to get too close to the Fermi energy. Or the closer the better.
I'll argue the closer the better, because then you reach the quantum limit earlier.
The paramagnetism.
Yeah.
Is it from occupied bands going down?
That's right. That's right. But you just lose the compensation from the diamagnetic response of the electron pocket.
So, but then in what sense is it? You emphasize the existence of the zero lambda level, but then
Yeah.
the signal exchange comes from occupied levels going down, right? Or maybe I misunderstood you. Where is the paramagnetic signal from?
Well, I mean, it is from the fact that you now have all these carriers in the... So, okay, there's a difference here whether or not you're talking about a metal like lanthanum or rhodium 5, where you have a rather constant chemical potential because you have huge bands that coexist. That's somewhat of a slightly different story from that of, let's say, niobium arsenide, where you only have tiny pockets around, and the chemical potential has to readjust to keep carriers constant. So these are somewhat two different things, and both will give you magnetic anomalies, but they're slightly different. This is now about the case where your carrier concentration is fixed, right? But there's no big bath to fix mu. So mu has to react.
Big bath. This first material that you talked about.
Yes, that's right.
Why is it paramagnetic there? Still a metal should be magnetic.
That's right. But what happens is now, instead of depopulating these lambda levels, your lambda level degeneracy factor pulls more and more electrons into this topology. So really this comes from the D of the lambda level, right? The degeneracy grows with increasing magnetic field, right? But mu is constant. So what happens is you constantly now transfer charge from the big bath into this mode, because you keep mu constant while it gets more and more degenerate. And that gives you the response. So if you then compute the derivative,
So what about all the negative levels that go down and reduce the energy? So it's square root of B times B. So it should be like a...
Okay, so what we have been looking at is simply only the model of a large electron pocket and the small pocket. You're absolutely right. If you have more other bands around, in general, the procedure can be very complex. I could even construct a case in which it kicks downwards. So for me, the main point is not necessarily that it becomes paramagnetic. You could also see, if you object to this, I agree.
I don't object. I just missed the explanation.
No, but the point is that it doesn't even become paramagnetic at the quantum limit. It only becomes later. It somewhat crosses zero. Okay, this is not the best way you can see this, right? It happens later anyways because it's kind of a change in slope. The way I think about this in more complex materials is as a compensation phenomenon. The main point I want to make is that at these types of quantum limits, you get an anomaly because the behavior fundamentally changes from that of massive bands to that of a massless band. And then whether or not it goes up or down, that really is a question of all of the other bands that you have around. I'm not sure there's a generic statement you could make. So maybe this is, I think, something I'm more comfortable with saying.
Sorry, just a quick question. I must have missed it. Can you explain the physical mechanism behind the angle dependence of the field?
Oh, that's this banana shape. It's essentially just that the quantum limit is very much angle dependent in such a system, right? So if you apply the magnetic field this way, you have a tiny cross section. So you will hit the quantum limit at very small fields, and if you go at a higher angle, this area here grows, right? Because it's the frequency that sets the counting.
Do you align your crystal? I mean, have you tested as a function of different orientations of your crystal also? Or
Yeah, that's this.
Okay, and that's your routine unit. Yeah, that's fine. Okay.
Exactly. Now, of course, I know that this is H parallel C, so, and this is H parallel A, so we have an aligned single crystal. Yeah. Okay, how about you? Well, one and then the other.
Yes, can you maybe go back and explain what this tiny pocket is? Because that I missed.
What the tiny pocket is?
Yeah, so or how this tiny pocket appears into your complicated structure.
Yeah, the whole point is that this is actually a Dirac pocket, and that's what sets this little pocket apart from all the other massive bands.
But I don't know what a direct pocket is.
Ah,
Sorry.
okay. Well, I mean, this is essentially what Dima had said. The whole point is that you have an E of K that is a twofold Okay, so now I'm not. Sorry. Yeah, I can't barely see this. Okay, I'm sorry. Okay, I can't really draw. Okay, maybe we discuss this later, but this of course important. It's sure. I hope it's permanent. If they have
And I know for sure.
It says dry erase should be good. Okay, sorry. Okay.
I can see that.
I was just making a cross anyway. But maybe okay. So okay. The Dirac pocket. This is of course an important pre-ingredient. Essentially, the statement is that you have a linear band crossing like in graphene, but just in 3 dimensions. So you have a linear dependence of the energy on momentum in all directions, but you also have, unlike the case that Jen discussed, you also have spin degeneracy. So every band is twofold degenerate, so you don't have a clear momentum spin, but you have all spins, or both spins available at each momentum. If you want, you can think of it as 2 Weil systems stuck on top of each other. That gets you quite far.
So it's like a Dirac point just with this.
In 3D, a Dirac point in 3D. Exactly right. Exactly right. Okay. Yeah?
How does the magnetization response look like for materials where you have like 20 or 30 Weil nodes?
Well, that's exactly this. So this has 24 Weil nodes. This is the beauty, right? So as soon as one goes into this state, you see a magnetic anomaly. Now, it's absolutely correct that what you would expect is that there's a series of magnetic anomalies, which are then slope changes on top of that when all of the other pockets go, right? But it just happens to be that in this particular material, because it's still in the tens of Tesla, it's very hard to measure magnetization in the hundreds of Tesla that you need to see all of the others. So in that sense, David's comment is quite good that maybe we should look for something that has a 2 Tesla pocket and 5 Tesla pocket. Then maybe we can see these kinks. And we can also look into your point, Dima, and whether or not all kinks are going upwards or if there's an upward, downward. This becomes then very complicated. But what I'm trying to say is that there is something dramatic happening there.
In this niobium arsenide thing with small firm surfaces, when you hit the quantum limit, you see, or if you know if anybody measured linear magnetoresistance, like this abricosive prediction.
This is magnetoresistance.
This is actually for that material.
Yeah.
It's not linear at all.
No.
No.
No. But again, I mean, the transport will be hellish because it's not just a single pocket. There's now, out of the 24, now you just to compute how many, but there's still 16 or so active. And they are not yet in the quantum limit, right? So I think this is just saturating magnetoresistance. Actually, it's a good question. I don't know the answer to in if the abricosive limit in a multiband system, is it kind of the last pocket, or what happens?
I think if I remember correctly, the mechanism relies on the screening being due to density of states.
Yes.
In the lowest Landau level.
Yeah.
So if you have bands that have B-independent density of states,
Mm-hmm.
and there are many of them, then the screening will still be just conventional.
Yeah, that's good.
Screening,
Yeah.
you won't see.
So then we need other materials with fewer cones. Really good. I'm excited. I hope you guys are too. Okay, I don't see much more than now is a good time to stop with the emails and take a changing gear. So I hope I've convinced you that it's at least worthwhile to consider, if you have a new material that's maybe topological, to measure its magnetization in very high magnetic fields. I love high magnetic fields, so this is good. Good for business. Next one is phase-sensitive detection. So I'll take a complete change of gear here, and I want to talk about quantum oscillation phases, kind of picking up where Dima has left off, well, with all of the addendum, which you had enough time over lunch to read through. So, okay, this is very simple, actually, in my point, is that if you have an electron, you can think about this also in real space, and this electron under a magnetic field goes onto a closed trajectory, and it comes back. And this trajectory will also enclose some magnetic flux. Now, real space, good old magnetic flux, right? And you can use the Bohr-Sommerfeld quantization, and you can compute this orbit, and this orbit will have, then this will have be quantized, and it will be quantized to integer values of some quantization index n, and it will also have some phase offset. And actually what will happen if you do the canonical replacement of the momentum is that you can here find a flux integral. So this will compute the amount of flux quanta that's enclosed in this process. And that's somewhat clear, right? If you think about this as a coherent wave, right? The wave starts here, the wave waves around this thing, it comes back, and the question is, does it interfere constructively, destructively, or not? And that will, if it needs to be constructive to be a stable orbit. That's one way how you can think about this. But at the same time, this looks exactly like what we've seen in David's parallel transport type pictures, right? I have a generic quantum state, and I start at some point, and then I look at all of the points, and immediately I would get a concept of the Berry phase, because as this object moves around this closed trajectory, it will furthermore accumulate the Berry phase, right? So, what phases does it now get? It gets the phase from the magnetic field, good, that's integer flux. It will also get the phases from this Berry phase contribution. So, it would be very nice if you could use this to now screen an unknown material. You just measure quantum oscillations, you look at the phases of these oscillations, and you see, does it have pi or not? And so then you can say, is it topological or not? This would be very nice. Unfortunately, it just doesn't work this way. Yeah?
That phase that you showed there, it contains, of course, our own home phase, but also there is the conventional, PDQ, sort of dynamic phase included. And
yes.
They're the same, essentially. I mean, up to a factor. So it's not one or the other. It's them together.
Absolutely. Well, in some sense, all of the phenomena go together, right? Because there's also, unless you have very strong, like complete spin-orbit coupling in non-degenerate system, there's also the spin factor that goes in. I mean, it's a one system, and you have to look for what are the stable states of this one system. You're right. It's not good to talk about one or the other. I completely agree with this. It's actually the main message of this section I want to send. Okay, let's look at this real quick. So you can measure quantum oscillations, for example, in cadmium arsenide, which is a rather well-known Dirac semi-metal. You can look at these, and you can then pinpoint where are the lambda levels. You can make these plots, and then you'll quite often find people extrapolate this to zero, and they look, where is the infinite field phase of this problem, right? And if you do this, then you could try and judge whether or not this is topological or not. But I really want to point to kind of a big heap of salt with this argument. As nice as it would be, it unfortunately doesn't work. And it has many reasons for why it doesn't work. But one is that there's many other corrections besides the Berry phase, which is what Dima just said, and I'll show you in a second. But it has another somewhat other problem from degeneracies. That is, it's not that much appreciated, but I just want to point this out in case you see these types of papers, that you have to look through how is this thing treated theoretically.
So actually, I said that our own home phase, the large one. So
yeah.
Here is a correction.
Yes.
So there is another large phase that comes from, PDQ. So
yes.
PTR that you wrote are canonical, right?
Yes.
You can write kinematic there, and that's dynamic phase that I mentioned.
That's right. That's
it's
right.
Of the order of our own home phase.
Oh yeah. No, that's also there for sure. Yes. So okay, it's true. Okay, so then technically speaking, I guess you can only say that the difference between two orbits is the flux quantum. You can't really count flux quanta with this. That's right, because you get this. Yes. Okay, I agree with that. But coming from quantum oscillations, usually we anyways think about the periodicity, at least from the fermiology point of view. But that's absolutely right. So let's think about this phase real quick. And so I just want to summarize. There's a huge body of work of this. So it started out with Schoenberg, and then there's more and more works. It's very difficult to summarize all of them. I need 3 pages of references. But I really want to point out to these 2 papers that I very much like. Okay, this personal preference without any completeness here. But okay, so what are the phases of these processes? There is the pi. If you want, you can think of this as the phase you get from a harmonic oscillator. You can talk about this as the Maslov correction, which is a question of the turning point of a particle as it changes its trajectory. This would be the good old 1/2, right? 1/2 of 2 pi. But then, if you really are rigorous about your semi-classics, then there's essentially 3 components that you all have to take into account together that add up to this phase. So there would be the Berry phase, and if you only had these 2, all of that I told you about would be true. There would be no heap of salt, and we would have a very good measurement. But there's another one that we've just discussed, and these 2 often come in pairs. It's a question of the spin orbit, which is associated with the self-rotation. And then there's a third one, which is the Zeeman phase. And since Yima talked a lot about the rotation, I thought, okay, I'll look a little bit more into this type of phase, which is associated with the spin degree of freedom, that unfortunately in this whole transport picture, you can't really ignore. Or fortunately, it depends on how much you like quantum oscillation physics. So Lifshitz-Kozevich has a very nice form for the oscillation component. Here it oscillates with some frequency, very nice. The main thing I want to talk about is this factor in front of it. There's some constant here, but here this factor here is usually called the Lifshitz-Kozevich damping term, and this sets the amplitude of this oscillatory process. And it is the product of 3 things, RD, RT, and RS. And I just want to walk you through these 3 things. These set the magnitude of your quantum oscillations. And the first one is it's the Dingle term. It's called Dingle damping, and it comes from the fact that there's a finite lifetime of scattering. It takes this particular form here. If you ever want to compute this here, the numerical parameters. The main point here is that when Dingle did these measurements, what was actually figured out is that somehow the quantum oscillations looked broader than what you would get from Fermi-Dirac broadening. This is why they translated this into an effective temperature that is even present at t equals 0, and it comes from the fact that, okay, this is now very small, but there's a finite lifetime of this state, so there's the tauing here. This is just scattering. The cleaner your system is, so then tau becomes very long, Dingle temperature goes to 0. Okay, this is a question of dirt. But all that dirt does is, since this is a real prefactor, it only dampens. So, to see quantum oscillations, you need to be clean. The other one is thermal damping. That's coming from nothing but Fermi-Dirac broadening. So now you lambda quantize your spectrum. So you have discrete lambda levels in 2D. In 3D, you have one-dimensional modes. It's actually quite similar for what I'm going to talk about here. And now you have to compare what is my level spacing. This is h bar omega c. And what is the temperature, the broadening of my Fermi-Dirac distribution. So what this one tells you is that essentially you have to be cold. So you have to be much colder. Your thermal energy needs to be much smaller than your h bar omega c. Now, I was counting on kind of drawing something. I won't. But the whole point now is really to see a very discretized, to be sensitive to the discretization of the electronic spectrum, your Fermi-Dirac function needs to be sharp. It at least needs to be so sharp as the features you want to observe. That's what this is. This is also a real factor. It does nothing but dampen your oscillations as you heat up the system. This is the reason for why we can't usually see quantum oscillations at room temperature, let's say. The last one is the tedious one. It's called spin damping, and it comes from the fact that if you have, say, a Dirac system, or you have a system which is spin degenerate, now you essentially have 2 Fermi surfaces in a high magnetic field, right? You have a spin up, a spin down, a majority-minority Fermi surface. And these 2, they will start to interfere. You can't resolve one but the other. You always see both together. And now it depends on the relative phases between these 2 objects in whether or not this interference is constructive or destructive. The sad part here, or good, it depends on your taste, is that this actually is an oscillatory function of an argument. So this thing can actually change its sign. So let's look at this, because that's very important what it entails. It entails the effective mass, m star. This is okay. You can measure this independently. This is an experimental quantity you get, right? Then there's constants of nature and pi's, but the tricky part is the G factor, right? The tricky part is really the difference in energy between spin up and spin down. And that's something that we really don't get too easily in complex metals. So this factor here is responsible for an effect that is called spin zero. It's a famous suppression of the quantum oscillations. It essentially happens when this argument happens to be pi's or multiple 2 pi times this. Then RS becomes zero, so the whole oscillation amplitude becomes zero and it's gone. It's called a spin zero effect. It's very popular in 2D materials, in organic conductors and things like this. But it's really dangerous because of its sign change. And the most critical part about this, I'd say, is that there is a huge chance for circular arguments. Because usually people use DFT to get to the G factor that they then use for their phase analysis that is then used to confirm DFT. So if your DFT is so good that it's correct, you don't need to test it. If it's test-worthy, you have a problem. And if you don't have DFT, you don't know where to start. So this really is a problem in using phases to get to the bottom of what is actually happening with your oscillations. Because, of course, if you happen to be in a case where the effective masses and the G and all of this brings in the other quadrant, you get a pi phase change. So one thing that's good would be if your effective mass are very light. That's one argument that a lot of my colleagues kind of use to get around this. You have an extraordinarily light system, so that m star over me is 10 to the minus 7. You really need a G factor in the order of 10 to the 7, which is kind of unlikely, right? But this is all judging. Okay, so with that, I just wanted to say, here are some of the references that I would recommend you to look into these if you want to look into what actually sets the phase. But if you're really just starting this, then really remember, the phase is tricky. That's my main statement. There's another piece of theory which I guess I won't have time to go through completely. I'll just mention what is the key point and then point you to the references if that's okay for you. And that's the question of degeneracies. So imagine that you have in your system somewhere you have one of these Dirac points, and then you have a Fermi surface around this. Then you will get an orbit that is, let's say, the semi-classical trajectory of the states that actually contribute to your quantum oscillations. Now, this is now a question of symmetry, how many of them you have, because you will likely have time reversal symmetry copies, you will have crystal symmetry copies, you essentially usually get a zoo of these copies. Not always, but sometimes. In the Weil case, for example, we had 16 copies of this Weil point. So there's not just one, there's actually many. But if they're crystal symmetry related, then their cross-section is the same. So they will all oscillate, but they will all oscillate at the same frequency, but not necessarily at the same phase. There's no such argument for the phase because it depends now on what is the symmetry of the orbit. So there will be a subgroup of your whole point group that leaves the orbits invariant, and other elements of the point group, there's still symmetries of the crystal, will map this orbit to that orbit. So there will not be a symmetry of the orbit. So now it's a question of what is the point group of your orbit itself, not of the crystal. And these two are different. In fact, the subgroup will be a question of field angle, because your field selects which states contribute to this, whether or not this is, for example, in a high symmetry plane or not. So, okay, there's a lot of math that you could do. There's tables that you can look up. Again, look in this particular paper. Then you can look into this. It depends really on which classes it falls. I don't want to go through this in detail. I just wanted to show this to you. That's what you would have to do, because the essential problem is that your measurement quantity is kind of a sum of oscillators, but the oscillators all have different phases. We know what you will measure is an oscillator with the same frequency. Frequency is all right, but with a different phase offset. And how to get from that thing that you measure to these individual lambda, which again encode in the area curvature as well as the other things of the orbit, is somewhat of a non-trivial problem. And you really need the crystal symmetry to find relations between these lambda, and that's what this paper did. Okay, I realize because of time this is very short. I just wanted to mention, because the main message here is phases are tricky. I want to point you to one of the first papers in quantum oscillations, actually by Dillon and Schoenberg, and it was measured in bismuth. Bismuth was the first material where quantum oscillations were found. And what they wrote is that, okay, we now have this new theory by Landau, it works fantastic, we understand this. But they also write, for bismuth, good agreement was found with the theoretical formula, except that the signs of the fundamental and the odd harmonics had to be reversed. So there is no Dirac or Weil semi-metal in the bulk of these bismuth Fermi surfaces, right? But still, it has the wrong sign, right? Now, in this particular case, it's really due to the proximity of these other bands. It has a tiny band gap, and it entirely comes from the self-rotation part. It just gives it a pi to very high degrees. It has nothing to do with bulk topology. Maybe a higher-order topology system, it's a different thing. So, quantum oscillation phases are dangerous. They're possible. They're dangerous. Take care if you do this. I'm not saying it can't be done, just saying it's dangerous. Okay. So, in that sense, I would call this with an X in that it's a great technique, but it's not something that we wanted. It's not a plug-in topology ometer. It's a very, very subtle thing that really relies on you having a good control over your electronic band structure. There's something else, temperature-dependent quantum oscillation. I just want to mention this really briefly, because it's a bit of fun, and it's the idea of how do we get around this. And so the whole point now is, can we do a phase-insensitive detection of our beloved crossing points, of two linear bands that cross, or Dirac nodal lines, or something in this direction. And here, the key point is that the effective mass of these systems becomes energy dependent. So what does this mean? So if you have a Fermi surface, this is the surface that differentiates between all closed and all open states. So it is essentially the isosurface of the energy of E of k is equal to some value of the Fermi energy. Now, if you say you increase this energy a little bit, then your Fermi surface will change a little bit, which also means that the relevant extremal areas of this object will change a little bit. So instead of some area, you will now have area plus delta area. And this is actually what defines the cyclotron mass. So the cyclotron mass is the derivative of area with respect to energy, as Dima showed. And that sets really apart Schrödinger electrons from Dirac electrons. I'll leave you with this math. It's really simple. It's 3 lines. You can do this after a couple of years even. You will find that in the case of Schrödinger electrons, this cyclotron mass is just a constant, and it's the effective mass. So that's good, right? In the case of Dirac electrons, that cyclotron mass actually itself depends on energy. So the closer your chemical potential is to the Dirac node, the lighter this cyclotron mass gets, okay? And so that is now giving you an angle of trying to experimentally see something from this. Imagine that you have a dispersion relation. Somewhere there's a chemical potential, and now you do this at finite temperature. So your Fermi-Dirac distribution is broadened by kBt, so that all these states in this window are occupied, all right? Then all these states in this energy window will contribute to your quantum oscillations. So in the trivial case, all of them will contribute. This is the right frequency corresponding to your area. These ones are a little bit bigger. These ones are a little bit smaller. So what you will find on average is the same frequency. Good. There's really no change. But in the Dirac case, there's a difference. Because now these states here, they're actually heavy. And these states down here, they're light. Because these are closer in energy to the node. So these have a smaller effective mass than these ones. And because the thermal damping actually depends on the effective mass, then the lighter electrons are, the bigger the amplitude is. So this will give you, if you average, an average slightly to lower surfaces, to smaller surfaces. It will pull this down, right? And because of that, in these types of linear systems, there's a temperature dependent of your effective oscillation frequency. And that's something you can actually measure. So you can then compute this more properly. What you will find is that your zero temperature frequency at finite temperature slightly renormalized. So it's the zero temperature frequency minus something that goes as t squared and a logarithmic derivative of the effective mass with respect to energy. This is beautiful because that object goes as 1 over e. It explodes as you are close to the Dirac point. So the closer your chemical potential is to the Dirac point, the bigger this phenomenon becomes. All right? And so the more easy it is to measure. Of course, if you're very far out, there's almost no more effect. Right?
So,
Yeah?
how do you distinguish that from just, regular Sommerfeld corrections to the Fermi?
We'll do that. We'll do that exactly next slide.
They look exactly like that.
No, they don't. Okay, there's two ways. If you have lanthanum rhodyminium 5, you have a big bath. There is no Sommerfeld correction. There's no Sommerfeld correction in a big metal. So it only becomes important in semiconductors when the density is so low that you have to adjust chemical potential. In that case, so this is perfect. This is just the slide to answer you. So in that case, all the frequency changes with temperature that you get is coming from this topological effect. However, if you're talking about isolated small pockets, actually Sommerfeld becomes important, right? In the Sommerfeld effect, simply because we need to keep carrier concentration constant, we also have to adjust our chemical potential in order to keep the carrier density the same. So there's also an effect coming from this. It's only relevant if you have very light isolated pockets. It is the same for topological or non-topological things. That really doesn't matter. It does matter in terms of what you put in for the density of states, but it happens for both. All right? So in this case, you actually need to correct for this. You have to subtract from your frequency the topological frequency. The beautiful part is that it looks the same, but this is bigger by about a factor of 5. So it's actually a much bigger contribution. I will show you. Okay, so we did these measurements, running out of time. Just saying, we measure quantum oscillations very, very precisely of 3 different materials: cadmium arsenide, famous Dirac semi-metal, lanthanum rhodyminium 5, the crazy thing I showed you in the beginning, with a tiny Dirac pocket and a big bath, and something bismuth selenium oxide that you can, in this case, really replace with p-doped silicon. This is, it's electron doped, so n-doped silicon. So whatever, this is just a topologically trivial, very beautiful semiconductor. Has about the same quantum oscillations. If you just do this brutal Landau level phase analysis, then you will find that actually cadmium arsenide, the Dirac semi-metal, has the exact same crossing point as bismuth selenium oxide, the semiconductor. That's already an example that this you can't use without knowing what you measure as a technique, right? They simply, in bismuth selenium oxide, all the states come from bismuth. It has a huge spin-orbit coupling. This is the only reason for why you get pi, or something very close to pi in this particular case. There's nothing to do with Berry phase in this particular material. So don't trust this, but trust the other stuff I'm showing. So if you now are very careful, you can measure the temperature dependence of your quantum oscillations, and the natural units to scale with this is just temperature. Temperature and effective mass. Both are measured quantities. There's nothing theoretical about this. So these lines here, the red Dirac line and this black line, they're actually just parameter-free calculation. This is just Sommerfeld textbook formula Ashcroft-Mermin gives you this black line, and Ashcroft-Mermin plus Dirac gives you the red line. So if you then just subtract the black line, again, this is Ashcroft-Mermin without any parameters, you end up with this thing, all right? So this is the topological phase change, the topological frequency change is a function of temperature squared. And on this Dirac prediction, which is the only effect left, you find cadmium arsenide, the textbook poster child of Dirac semi-metals, and lanthanum rhodyminium 5, the crazy stuff that we don't understand, and they all fall on the same slope. Not somewhere, but exactly on this line, whereas the trivial bismuth selenium oxide has nothing left after you subtract, again, this mathematically computed line. So this is really not a fit, all right? This is just Sommerfeld from Ashcroft-Mermin. You subtract this, and then you get that. So this is actually a really nice tool to fingerprint unknown orbits. Yes?
What is the topological frequency that you were saying, like on the y-axis?
Yeah, that's the temperature dependence of the frequency. So if you measure the frequency, I think here you can see, you have to really squint. On this projector you don't see, but you can actually see this in the raw data that the peak positions slightly shift. So then if you do the Fourier transform at every temperature separately, then you will find that the position of the frequency actually shifts. And so there's a temperature dependence to the frequency.
The frequency of the oscillations.
Exactly. The frequency of the oscillations is temperature dependent, in low carrier density semiconductors just for the Sommerfeld effect, and in all topological, not all, but in linear bands, because of this correction. We call this, of course, topology so that we can sell it. David didn't buy it, but that's okay. But in general, this is sensing linear bands with a tiny pocket. Yeah?
This on the next slide, just to be clear, you subtracted the Sommerfeld term from the topological material.
Yeah, that's right.
But did you subtract anything from the trivial material?
Yeah, the same. So sorry, so these two, cadmium arsenide and bismuth selenium oxide, these two have both, because they're low carrier density, these have Sommerfeld and they have the topological part. So we subtract Sommerfeld from this, Sommerfeld from that, but not, of course, on the lanthanum rhodium pipe. You can do it, but if you compute the Sommerfeld, it's inversely proportional to carrier density. So it's zero. It really is zero, because there's 10 to the 23 carriers. So the Sommerfeld correction here is negligible. So then the uncorrected lanthanum rhodium 5 falls onto the same line of the corrected cadmium arsenide bismuth selenium oxide. So, but again, in both cases, unless you have something very weird, which is somewhat intermediate things, where Sommerfeld is kind of a little bit relevant, but not yet quite, and you don't know your carrier density, then you may need to know some density of states so that you know what to correct for. But let's say in somewhat well-behaved objects, this is nice. The other thing is that this becomes, this is a temperature-dependent effect, right? So you might say, ooh, but what if my effective masses are very high? Then I only can see this at low temperatures. But the beautiful thing here is that this is also scaled by the effective mass. So if my system is very high, this parameter actually goes as the effective mass squared. So it's really independent of your effective mass. If you have something very light, you can see them up to 100 Kelvin. That's great. But really, the temperature scale you need is always kind of at the half point of the LK. So you can even do this in heavy fermions, which is something that we're doing essentially right now. Okay, that's it. I hope I'm somewhat on time. I did not do any of the self-advertisement, even I should have done. So here you can take a look at all of the other fun things that we do. Lots of experimental things, micro nano fabrication. It's really the best. Take a look. But what I tried to tell you is to answer partially the very big question, I only had 1 hour, of what could be possible routes to experimentally find topological systems if you don't know much about the material. If you're really working on experimental materials discovery, I would really urge you to look into the magnetic anomalies at the quantum limit if it is accessible to you. Phase sensitive detection, use it, but with caution, right? Temperature-dependent quantum oscillations, I kind of would put as an orange wiggle. It's really nice. It's a good fingerprint. It only fingerprints linear bands, so there might be a gap. We don't know, right? It fingerprints linear gaps, but together with tiny pockets, this is actually, I would say, rather strong. I put the orange wiggle mostly because this is really a tiny effect. This is a 4% correction or so of the frequency. So it doesn't really qualify for my topology or meter that I really want. So it's a story to be continued, but I think this is the fun part.